Okay. So let's today's lecture with a new topic, that is unit 7, and the topic name is unit name is polyphase circuits. So first question is what is a polyphase circuit and why it is needed at all? So polyphase circuit is basically the circuit which have more than one phase. So what we have learned in the AC system up to this lecture was a single phase AC system. What does a single phase AC system mean? Means compared to you will have only two wires of the system like this, and if you plot a graph, you'll get a graph like this. It would be a more sign like the figure is not exactly what I want to need, but this is the scenario. So you have a two line system where the one line is known as the line and the other line is known as neutral. So using a two wire you can connect anything. Okay, for an example, if I want to connect something over here, that would be two line. Okay, this is my generator, let us say, and I can connect something using this two line system. This is a bulb for an example. This was the single phase circuit. How to generate single phase? We have seen that video of a generator in which we have seen how to generate a single phase. There is a magnetic field present, and inside this magnetic field, what I'm going to do is I'm going to rotate a coil, okay, like this, using some external mechanical energy. How that external mechanical energy comes? It comes from either the turbine. Okay, the turbine can be rotated through like hydropower. It can be a thermal power, a steam engine, or you can say steam turbine, or you can have a wind farm. Using any of this means, you can rotate this turbine, and that turbine is a mechanical energy which will rotate this coil. As this coil is rotating inside your magnetic field, it will produce a current inside this coil, and that current is basically what we are using is first it will produce an EMF, and if the circuit is connected it will produce a current. So that's about the single phase. Now there are a lot of issues with the single phase. That's why we have moved to a new system that is known as a three-phase system that we use currently throughout the world. So what is a three-phase system first? So mainly a three-phase system have like either it will have a three-wire or it may be a four-wire system. Okay, why I will say a maybe, the answer will get later on. Okay, if it's a three-wire, there would be three lines, and if the four-wire, there would be three lines and one neutral. What does this mean? Like three line, four line. What does this mean? So between any line and neutral, or between any line to line, you will get some waveforms. Okay. For an example, in this four wire system, if I take the let us say waveform between this line to neutral, I'll get this kind of waveform. And if I get the waveform of other line to neutral, I'll get the different waveform that would be partially ahead of this or behind this, like this, and the third wave would look like something this. So this is a three-phase system where you have your three different voltages or current waveforms, okay, leading and lagging behind each other, leading and lagging behind each other by some phase angles. Okay, so depending on the number of phase, polyphase is number of phase, like how many I don't know, but it's more than one. That's the thing. But throughout the India or throughout the world, we generally use three-phase system. So we are going to learn that as a polyphase system. A three-phase system can be called as a polyphase system. So in this chapter, we'll see a very basic concept about the polyphase circuit. Okay, so let us start with the polyphase circuit. So the generator producing a single phase supply has only one armature winding. That is the first thing. See now how it is generated. So here you have only one winding, but if it's a three-phase system, you will have three separate coils like this. The one coil would be like this. The second coil would be with some angle like this, and the third coil would be at some other angle. And this three coil will be rotated at the same time with the same turbine, using the same mechanical energy. Okay, so on single shaft you will have three different winding, and each winding will have like two ends. So each two ends, like that two ends are connected with each other, in different formulation, and it will generate this either 3-line system or 4-line system, 4-wire system. So that's the first thing. But if the generator is arranged to have 3 separate but identical winding displaced 180 degree apart and rotate in common magnetic field. Okay, so the angle is given now. This angle between any two coil is 120 degree apart and rotated in a common magnetic field. The field is still same. It produces three voltages of the same magnitude and a frequency. The voltage, magnitude and frequency will be same, but that voltage and magnitude would be displaced by 120 degree electrical form from one another. This is called a three-phase system. Okay. So see how it is done. This is the example of single phase system where you have N, S, you have one coil like this. So whenever this coil is in this position, it will produce a maximum flux, minimum flux, and then when it cuts at 90 degree, it will produce a maximum. Sorry, when it's like this, it will produce a maximum flux. When it is at 90 degree, it will produce a zero flux. What we have in the, like, let us have a two coil A and coil B. So when this coil is like now this both of this coil are connected to the same shaft. So what happens when I rotate the shaft? These two coils move at the same time. So if I say this condition is stationary right now, the flux in phase A is maximum compared to phase B. So at this time, what will happen? The phase A will produce a maximum flux and phase B will produce a minimum EMF. Like EMF produced would be different. Why? Because the flux linkages are different. Flux is linked at maximum at the one and flux link is minimum in the other coil. That's why we see this different. Now if I try to rotate this, the flux will gradually increase in the one and gradually decrease in the other one. So the flux will decrease in one and increase in one. So EMF will increase in the one and decrease in the one at the same time. Now at some point of time, this B will be in this position and A will be in this position. Okay, the position will be changed. At that time, what will happen? At that time, B have a maximum flux, so I'll get this point, and A has a minimum. That's why I get zero EMF on that side. So see, this is how a polyphase system works. Now, if you have, so if you measure the difference between these two, you will get a 90 degree difference. Okay, because we have a 90 degree over here. That's why when that two takes maximum minimum, that would be 90 degree apart with each other. Same way in three-phase system, we have three coils. So here the flux linkage in this coil is maximum right now. Let us say, okay, this is maximum right now. Let us take this one. This is maximum right now, phase A. This is maximum right now. But at the same time, the flux in this two are similar but opposite in direction because the flux lines goes like this. So flux cut would be like same, okay, but one current is in the one direction and the current in the other will be in other direction. Why? Because right now this coil is positioned like this, okay, and I am rotating in this position, but the coil in the other coil is like moving like this. So it is going towards n pole, okay, and this C1 is again going on this side, but it is going at the maximum point. So what will happen at the same time? The flux linkages would be same, but different in the direction. So after some point, one would be increasing and the other would be decreasing. You can see. So this is the point where this position occurs. The flux would be same. So EMF would be same. Okay. But as soon as you go to the next position on this side, the change, this C1 is coming in this close. So the C phase would be having like it is EMF generated would be more, and at the same time the EMF generated in the B would be get weakened. Why? Because B is moving away from the pole and C is coming near the pole. The same time AB is also going away, so A will also start to decrease. So this is a three-phase system where a three waveform will be there, and each waveform would be 120 degree apart from each other. Why? Because we have a 120 degree angle over here. Okay, though it looks like 60 degree. Okay, if you look at here, it looks like 60, but it is actually it's 120 degree. So this is how a three-phase system works. This is how a three-phase voltage is generated. So what I'm doing, I'm rotating all the three coil with 120-degree separate, like 120-degree apart in the physical. Like when the coil is wound, it's wound in such a way that 120-degree angle is made between two coils, and then it is rotated in the same field. So what will happen? At any point of given time, one coil would be producing a maximum EMF and another two would be producing the lesser EMF compared to that. And when it start to rotate, it will produce a EMF according to the flux cut. But this is why we get this 120-degree angle or 90-degree angle in the two-phase system. But we will be discussing three-phase system in details throughout this course. So if I want to write an equation for this three, what I can write it, first equation EM would be first equation of phase A can be, let us say, Em sin omega t. Then the other two equation can be written like this. Okay, if I take this as a reference, this point as a reference, then sin omega t, Em sin omega t is the equation for the phase A. Then 120-degree apart. So 120-degree behind phase A is phase B. So phase B will become Em sin omega t minus 120. Okay, and phase C is 240-degree behind this. So it can become omega t minus 240. Sometimes you make these equations like this. Em sin omega t, where you will get omega t, let us say minus 120. The other would be Em sin omega t. And the third equation can be Em sin omega t plus 120. Okay. You might see this equation as well, where omega t plus 120 and minus 120 is given. So at that time, what we do is basically, let us take this point. So here, this is 120-degree behind and this one is 120-degree ahead. I can say like that. Okay, that's why you might see it as like either minus 240 or plus 120. That's good. No issue in that. Okay, both these are correct. Most of the time we'll be following this, but sometime you may see this in life somewhere, and that's also correct. The one is 120-degree behind and the other one is 120-degree ahead. We can say it like that. Okay, so that's just the reference window from which phase I'm taking the reference. That's the important. Now, what are the advantage? First, what are the advantage of this system? First advantage is constant power. In a single phase circuit, the instantaneous power varies sinusoidally from a 0 to peak value at twice the supply frequency. So what happens is the instantaneous power, okay, we have plotted that graph, V into I. Okay, V into I, we done that V into I. If it's the circuit of R, we get a pulsating power like this. We have seen that. You get the power that looks like this. Okay, this is Vi. So Vm Im sin omega t was the equation, like sin omega t to sin omega t, that was the equation, and you get this kind of value. So this is the issue. You don't get a constant power. Like power is constantly generating and decreasing. However, in a balanced three-phase system, okay, balance is very important one. We are not going into that right now, but it's a very important word. The supplied power at all the instant would be same. All the instance of time is constant. Because of this, the operating characteristic of three-phase apparatus in general are superior to those of similar single-phase apparatus. So what we'll get is a power graph like this. Okay, how do you get that? We'll see that if it is there in your course. We'll see that later on. Otherwise, this is the scenario. So the performance of your apparatus would be greater compared to your single phase system. Why? Because in single phase system you have pulsating power, but here don't have the pulsating power. Then what is the second advantage? The second advantage is greater output. What does that mean? The output of a three-phase machine is greater than that of the single-phase machine. How can I say that? For a given volume and weight of the machine. In other words, a three-phase machine is smaller than a single-phase machine or the same rating. So what he mean is, if I have, let us say, a single-phase motor, that's the size of the screen. Let us say, for an example, this computer screen, any computer screen. In that case, in the same size, if I have a three-phase machine, the three-phase machine would produce a more power compared to weight or more power compared to volume. So if you take this same size of machine, both the machine, in that case your three-phase machine would be outperforming single-phase machine. So output power would be greater in case of three-phase machine. That's the thing that you want to say. This is the distinct advantage of three-phase system over single-phase system. That's why we due to this all advantages we are moved to three-phase system. It is cheaper. How it is cheaper? The three-phase motors are much smaller and less expensive than the single-phase motor because less material is used. Moreover, three-phase motors are self-starting. This is about motor. Okay, these motors are self-starting. They do not require any special provision to get them started. However, single-phase motors require internal starting device. What does that mean? You have a fan at your home. तुम्हारा बद्दाना घरे fan छे. Now in fan, sometimes it happens that fan slows down. So at that time, if you call the technician, he will say a capacitor बदलવું પડશે. What does that mean? A capacitor बदलવું પડશે. So that device, that fan is inductive kind of nature. So in that your voltage and current is 90-degree apart, and that's why it cannot auto start itself. So what you have to do, you have to start it by providing a capacitor. So you balance that inductive load, you lessen that inductive load, and there is a centrifugal switch in some fans, so it will automatically cut out at a later stage. We are not going into that deeper, but what I mean to say is, to start the motor, single phase motor, you require some additional jerk, and that additional jerk can be provided using your hand or mechanical movement, or the other option is by changing the vector of your fan or any motor using a capacitor. So capacitor starting method is used generally in single phase motor. Like mechanical motion is not used at any time. We only prefer the capacitive method. So what we do is we connect a capacitor in parallel with your inductive motor, or let us say inductive load, or let us say motor, single phase motor. That way you can start the machine. But if it is a three phase machine, it does not require a capacitor at all. It will auto start. It can auto start. Okay. The next point is power transmission economics. What does that mean? So transmission of electrical power by three-phase system is cheaper than that of single-phase system. Even there, three conductors are required instead of two. So if you want to power transfer using a single-phase line, you will require two wires, one being the line wire and the other one being neutral. But if you try to power transfer using a three-phase system, you need either 3 wires or 4 wires depending on the system. So though a 3 conductor is required, but the power transfer would be like compared to your single phase would be much more higher. For example, to transmit the same amount of power over a fixed distance at a given voltage, the three-phase system requires only 3/4 of the weight of copper than required by single-phase system. Okay, how much is only required? 75% of the material which would be required to power to transfer the same amount of power using a single-phase system. If you want to transfer the same amount of power using three-phase system, you would only require 75% of the copper. Why I'm saying copper? Because copper is very costly, and it is the precious material, and it is very expensive. That's why if your material required is great and the power transfer is higher compared to the single phase, then this basically advantageous point. This means a saving in the number and strength of transmission towers. So what you will have is number of less transmission tower. At the same time, you will get a superior power transfer. So why this strength of transmission tower, like number and strength of basically if I add a weight, I want to hang a weight from something, then that something has to be like heavier. So if my weight is less, then the tower can be like strength can be somewhat less compared to the required to having a single phase transmission. That's why it is given strength of transmission tower and number of transmission towers. Then three phase rectifier service. This is very important point. Rectified three-phase voltage is smoother than the rectified single-phase voltage. As a result, it is easier to filter out the ripple component of three-phase voltage than that of a single-phase voltage. This is especially useful where a large AC power is to be converted. Let me draw it like how it looks like. If you have a rectifier in single phase, like I am having a full wave rectifier in single phase circuit, then what I'll get is this. This is my DC that I have generated using single phase system. But if I use a three phase system, what I'll get is this. So if you see this, okay, see number of pulses are no doubt higher, but the transition from one pulse is very small. So I can easily filter this out. To filter out is very difficult task. The higher number of higher the amount of pulse in this way. We say this as a TDH. We are not going into that, but the filtration required over here would be much more larger. The filter size would be larger here, and the filter required to smoothen this out would be very compact size. And itself, if you see this is in a very narrow band. This is very narrow band of the voltage level, but this is a huge band of voltage level. So voltage will vary from 0 to 230, I can say, not 230 exactly, 325 is the voltage level. But in here, it will vary only in some portion, like how I draw this. So if you look at this, when it will be filtering out, whenever this point is there, this point, it will be filtering out from that point only. So you get only this pulses. That's the point. So rectifier is very easy and filtration is also very easy in case of your three-phase system. That's why we have moved to three-phase system. Still there are so many points. We'll cover it one by one. Next point is miscellaneous. What does that mean? Other advantage of three-phase over single phase. A very basic is a three-phase system can set up a rotating uniform magnetic field in a stationary winding. This cannot be done with a single phase current. So this is related to that self-starting. A three-phase system can set up a rotating uniform magnetic field. So if this is not possible using your single phase, and that's the basic reason why your fan does not start without a capacitor. The three-phase motor are more efficient and have a higher power factor than the single-phase motor. So single-phase motor generally have a power factor somewhere around 0.7 to 0.75, and a three-phase motor have a power factor somewhere from 0.8 to 0.9. Generally it is 0.85 to 86. So a power factor is higher. That means your reactive power consumption would be very less. Like reactive power transfer would be very less, and all the line that you have in your system can be used to transfer the active power, which is actually needed, which can be consumed. A knowledge of three-phase power and three-phase circuit is therefore essential to an understanding of power technology. Fortunately, the basic circuit technique used to solve single-phase circuit can be directly applied to three-phase circuit. So equations are almost same. It is because the three phases are identical to and one phase represent the behavior of all three. That means if I represent a single phase out of this three, and if you have a single phase that looks like identical, okay, if I remove this 2 from here, like phase B and phase C, then this phase A matches with this phase A. Okay, it will start at 0, it will get maximum at 90, it will get 180, when it gets 180 it will be 0. That all point related to same. That means you can apply the same equation that you have used in single phase in three phase system, though it would be a little bit modified, but you can apply the same techniques. Now let us understand the phase sequence. What is a phase sequence? A three-phase system, there are three voltages having the same magnitude of frequency displaced by electrical angle of 120 degree. We have seen that. Okay? They are attaining their positive maximum value in a particular order, and that order is basically my phase sequence. Okay? So for an example here, if I have drawn this, here my phase A is first, phase B is followed by that, and phase C is followed by that. So phase A is leading, phase B is behind A, and C is behind A and B both. Okay, so this is in particular order, and that's nothing but my phase sequence. Why phase sequence is important? Okay, why it is important? For let us have an example. Why it is important? So if you have a motor, a three-phase motor, let us say I have a three-phase motor. Okay, here there are three connections. Let us say the connection named are L1, L2 and L3. Okay, now I have connected three-phase system over here. The phase sequence is this R, Y, B. Okay, phase A, phase B, C. The same way I can say, let us say R, Y, B. So R is getting maximum first, then Y and then B. So if this three phases connected in this way, then motor will rotate in one direction. Now let us assume I have changed either of these two. Let us say I have connected B first and Y later on. Okay. Again, the generation is like this R, Y, B. But what I have done, I have connected R followed by B and then Y in the L3. So immediately your motor will start to rotate in this direction. Okay, that's why phase sequence is important. So this is the reason, because in here there would be three coils like this. Okay, one coil would be L2, L3. Okay, it would be like this. So this is L1, this is L2 and this is L3. So if I change this phase like this, then L2 will get max later and L3 is first. So your motor start moving in the other direction. That's why phase sequence is important, like which phase comes after which phase. So the order in which voltage in three phase attain their maximum positive value is known as phase sequence. Let's have an example of this system. Let us say this is a generator. This is a three-phase generator. So you have this three coil, 1, 2 and 3. Now this three coil is connected in this way. One single point is connected at the same point and the other three are connected to the outgoing line. That means I have a central connection over here. So I can say this is a star connected system. This is a star connected three-phase system. So in star connected system, you will have a three line and one neutral wire. In star connected system only, you will get this three line with one neutral. So this is a four wire system basically. What are the four wires? This is the first, second and third. Generally three wires, three line is known as R, Y and B. And the fourth one is known as neutral. So RYBN is this name of the system. So how the line is connected? So see, this is my first. Okay. So the first coil is connected between neutral and line 1, and I can say the terminal is R1 terminal. So current flowing through this coil would be IR. Then the second coil is connected in the Y phase. Okay. So this is a generator side. So that's why this is a generator side. That's why you see this current flowing from neutral to line. So why this, from where this current came from? From neutral? No, it is not coming from neutral. Basically, it is coming from that magnetic field that is being present over here, and the sum over this point would always be 0. That means IR plus IY plus IP would always result in 0. Okay, so no current is coming from here. When the current is going out like this, at that time these two current might going in. That's the scenario. But time being, it is shown like all the current are going out. Okay. So now let's understand what are the different scenarios. What would be the different voltages over here? So first, you are clear about trigger. Now I have four wires. So if a current is flowing from a neutral towards the line, this current is known as phase current, or you can say line current. Okay. Then there are different voltage levels over here. You can see one voltage can be measured between this R and N. The other voltage can be measured between R and Y, and a third voltage can be measured between R and B. So if it is between your R and N, then it is known as ERN. Okay, it's represented over here. Same way, it is between R and Y, then it is known as VRY, and VBR between B and R. Okay, so what is this? These are known as line to line voltages. Okay. Between any two phase, R and B or R and Y is phase. So line to line voltage is the term for this voltages, and this is line to neutral. This is line and this is neutral. So if it is between line and neutral, then it is known as line to neutral voltage. And line to line voltage and line to neutral voltage can be different in a three-phase system. Okay, we'll see that later on, like how it is different. But these are the basic terminology. Now let us understand. The EMF across each winding is called phase voltage. Okay, if you don't read it as a line to neutral, you can also say it is a phase voltage. If it is ERN, I can say it is a R phase voltage. They are denoted by ERN, EYN, and EBN. The voltage between any two line is called a line voltage. So this is line voltage or line to line voltage. They are represented by VRY, VYB, and VBR. Okay, only three because there are three lines. Similarly, the current flowing in the each winding is known as the phase current. So this is my phase current. Going through any coil is phase current. The phase current is flowing in each line. So whatever is the phase current inside the coil, same current is flowing inside a line. If it is a delta connector system, then the scenario would be different, but here it's not the case. So whatever is the phase current, that same current is flowing in the line. So IR is flowing in the R phase, I can say. Okay, since the system is balanced, I have assumed the system is balanced, that's why I can say IR is equal to IY is equal to IB is equal to I phase. So I phase is the representation of any phase current. IL1, IL2, IL3 is equal to IL, and then IL would be same as I phase. Okay. Then ERN, EYN, EBN is equal to E phase. This is a phase voltage, and VRY, VYB, and VBR is the line voltage. This is a balanced system. That's why I can say it like this. Okay. This is just a quantity, RMS values of each quantity. These are the RMS values. The relation between line current and phase current. Now let us understand the relation between line current and phase current. So here from figure 1 it is clear IR is equal to IL1. Now let us see where is IR. IR is here, IL1 is here. So IR is equal to IL1. Why? Because whatever is the current inside this coil, that same current would be flowing through this branch. This is a series. So that's why I can say line current is same as phase current. That's why it is written like this. IR is equal to IL1. That's why I can say phase current is same as line current. This is only true for star connection system. If it's not star connected system, that this won't be true. So line current is equal to phase current in star connection system. That's the point. Now let's understand the relation between line voltages and phase voltages. So this is about current. Now let us understand about voltages. It is seen from figure that in star connection there are two phase winding between each pair of line terminals. Okay. So see what he means to say is, if this is line 1 and this is line 2, there are two windings in between. Okay, so the line to neutral voltage and line to line voltage will be different. Okay, so ERN and your VRY would be different. That's the point. Now how different it would be? Since similar end of the two winding are connected together, the EMF across this oppose each other, and that instantaneous value will have opposite polarities. Okay, since similar ends of this two winding are connected together, the EMF across each of them opposes each other, and their instantaneous values will have the opposite polarities. So what does it mean? If I have this ERN, okay, and if this is EYN, now the neutral terminus is this. So how basically where my EMF is generated at this point, my EMF generated at this point and this point. This is the neutral point, common point. So this voltage and the voltage between these two will oppose each other, and due to this opposition you will get a resultant that is different than this. So polarity is different. That's why this two will go, like it will try to push away each other. Therefore, the RMS value of line voltage between any two lines will be obtained by the vector difference of the two phase voltage. So how to get that? So to get that, let us say this is my VRN, okay, not V, let us say ERN, and my, let us say this is my EYN. So if I want to find out the equivalent, then it will result somewhere over here. Okay, so it would like this. So I am going to perform a vector, and based on that vector I'll get the correct voltage, line to line voltages. Okay, now let us see that. See, this is the scenario. This is my ERN, this is my EYN, this is EBN. Okay, so R phase 120 degree apart is Y phase, and 120 degree apart from this side is B phase. Okay, so all the phases are 120 degree apart each other. Now due to the load of the need, like load, the IR may be at some angle behind, but if the balance system is there, the same way the phi phase behind would be like the angle between my voltage and current would be phi. Same way for the B phase. Okay, so this is just to represent an inductive load. If a resistive load is there, this IR will be on ERN itself. We have seen this with this single phase. What are the relation between the terminal R and Y? Now I want to find out the line voltage VRY. How to find out that voltage? So to find out that voltage, you are going to perform ERN plus ENY. Why ENY is written? See, the voltage between neutral and your line is like, this is a EMF generator. So this is my Y point, and this is my N point. So if I want to perform a sum between this 2 points, R to Y, so what I'm going to do? I'm going to do ERN plus ENY. Okay, so NY. So I can say that is minus EYN. Okay, what I have done is ENY, and that is nothing but minus EYN. So VRY is equal to ERN minus EYN, and that is nothing but a phase difference. So line voltage is equal to ERN minus EYN, two phase to phase voltage. So one phase minus other phase would result in this VRY. If you are looking for VYR, in that case EYN minus ERN would be the similarly for Y phase like YB and BR line. Hence, it is clear that in a star connected system, the line voltage is obtained as the vector difference of two corresponding phase voltages. This is shown in figure below. So this is the figure. So see, this is my VRN, and this is my VYN, and this is my VBN. Okay, this is the basic phase: R phase, B phase, Y phase. Okay, now how to get the equivalent? So we know this equation: ERN minus EYN. So this is my VRN, this is my VIN. So negative VIN would be in this direction. This is my VYN. What I need is minus VYN or VNY, I can say. So this is my VNY, 180 degree apart from VYN. So this is my VNY, and if I perform a sum between that two, ERN plus ENY, same with this is V. So if I perform a sum between these two, I'll get this VRY, that is 30 degree ahead to line to neutral voltage. So line to line voltage is always 30 degree ahead of line to neutral voltage. That's what this figure shows. Okay, and you can get this quantity like this: VRN minus VYN, or you can say plus VNY. This is the phasor representation of the line to line to neutral voltages. This is line to neutral. Red is line to neutral, blue is line to neutral, yellow is line to neutral. The black is the resultant that we will get. Again, the resultance is also 120 degree apart. You can see here your phase to phase voltages between RY or YB is again 120 degree apart from each other. Okay, same as the line to neutral. Like line to neutral is 120 degree apart. This is YN, this is RN. This is 120 degree apart. Same way, your line to line voltages would be 120 degree apart in all these three phase sequences. This is shown in below, and VRN, and this written just why we have taken it like this. Okay, since side of the parallelogram are equal length and angle between two phase voltages is 60 degree, the line voltage is given by VRY is equal to VRN minus VN, that is 2 V phase cos 60 by 2. Okay, how that come? We know that angle is 60 degree. We know that. That's why we can do this. Phase voltages would be same. Okay, how it is same? the quantity, maximum quantity, that's balance system, that's why the maximum quantity will again that would be same. That's why we can write directly 2 V phase cos 60 by 2, and from this we can say the relation between my line to line voltage to phase voltage is line to line voltage is root 3 times phase voltages. Okay, line to line voltage is higher than the phase voltage. You can see it over here as well. This is my line to line, so quantity of line to line is higher than the phase. Okay, so this is the quantity. How like what is the actual quantity? It would be root 3 times of this line to neutral voltage or phase voltage. Similarly, for VYB and VBR, it would be three phase. So in general you can say your line voltage VL is equal to root 3 times your phase voltage EPH. Thus, in balanced star connected system, VL is equal to under root 3 EPH. So this is the relation between the voltages. The relation between current is very simple. Whatever is the line current, same as the phase current. Phase current and line current are same, but in case of your voltage, that's not the same, and that too would be different. Now let's talk about the power. So total power would be 3 times power per phase. So that's why the 3 is here. So 3 into V phase I phase cos phi. You can represent that 2 in terms of line. So it would be 3 into VL by root 3 into IL cos phi, and it will result in 3 under root 3 VL IL cos phi. Okay, VL is line to line voltage, IL is also line to line voltage. Okay, so you know that at your home you say મારા ઘરે single phase meter છે, મારા ઘરે 3 phase meter છે. What does that mean? If you have a single phase meter at your home, whole GEB or whole power system of India is based on 3 phase system. So if you are using a single phase meter or single phase at your home, what does that mean is there would be a 3 phase like this along with a neutral, and in your society or your home you are only getting one line and one neutral, and that's why between one line and one neutral you will get 230 volt RMS values. Okay, but if you have a 3 phase system and if at your home you measure the phase difference between two line like line to line voltage, it would be somewhere around 440. Okay, even you can calculate this. How you can calculate this? Use your calculator. It is root 3 times your neutral. So let us find out root 3 first. That's square root. I just program and calculate. Where is it? Yeah, it's not available. Okay, just do under root 3 into 230. Whatever you get is this voltage. This is wrong. It's a 440, not 440. So at our home, you will get actually. Why did you not write it correct? 440 volt, somewhere around that. So between line to line, it is still 440 volt around your home. Like if you look at the lines going outside your home, that would be 440 volt line. But that is between two line voltages. But if you measure a line to neutral, it would be only 230 volt. Okay, it should be noted that phi is the angle between phase voltage and phase current and not the between line voltage and line current. Okay, see this phi here is the angle between phase voltage and phase current and not between line voltage and line current. At that time the current would be like the angle would be different. Okay, why this would be different? Because line voltage is 30° ahead to your phase voltage. Okay, we have just seen that over here. It's 30° ahead. Okay, that's why the angle between phase is phi and not the line. So this is the equation using which you can calculate the power, total power. Okay, you can say average power, not average power. It's your instantaneous power. Okay, in your 3 phase system. So it would be 3 times into power per phase. Same way, there is one more system Similar to this, there is one more system, and that is known as a delta system. So in this delta system, what is the difference is the coils are connected with each other and there is no central point or no neutral point. So what happens here is the phase voltage is between, there is no neutral, that's why where I can say a phase voltage is equal to line voltage. Okay, the phase voltage and line voltage would be same. But if the current is represented like this, let us say this is my IY and this is my IR. So resultant current in this line would be IY minus IR. Okay. So this is coming in and this is going out. So I can say IY is coming in and IY going out. So my line current, this is my line current. Okay. This is my phase current. So line current is different than the phase current. But the phase voltage and line voltage, okay, V phase and V line would be same. So this is the generalized representation. Now let us understand the relation between these three. So here IR is equal to IY is equal to IB is equal to I phase and line voltage IL1, IL2 and IL3. Okay, where are IL1, IL2, IL3? IL1, IL2 and IL3. Difference between my currents IY minus IR or IB minus IR or IR minus IB depending on the phase. Okay, so that's the difference. So relation between voltage is very easy. You can say your ER is equal to VRY is equal to E phase. So line voltage and phase voltage are same throughout this delta system. As the in star, your current was same for line and phase, same way here voltages would be same, the current would be different. So now we already know the relation between relationship between current in line and phase. So we can plot the vector diagram like this. Okay, now see, this is my voltage, this is angle phi by which my current would be lagging, and this is my IR. Same way, this is my VBR or EB, and the current of that is this one IB. Same way, there is IY over here. So if I want to find out IL1, that is IR minus IB, what I have to do? IB is going in this direction, so I have to take negative IB, that would be this negative IB, and then a sum between that two, so we'll get this IL1. This is my IL1, which is higher than the phase current again, but right now it is lagging behind IR. So the voltage one in star that is leading, right now it is lagging. Okay, it's behind, and phi actually not phi, it is by 30 degree. So this is the relation between line current and phase current in your delta connected system. Now let us see the equation. The equation you will get is again IR minus IB to result in 2 into I phase into cos 60 by 2, and at the end you will get the same relation that you have getting in the that scenario for the star. This is true for star, and delta you get IL is equal to root 3 times I phase. The only difference here is line was leading here, here your line is lagging by 30 degree. So leading compared to phase, here lagging compared to phase. So this is the relation in delta. So in delta you will get the current difference, in line you will get voltage difference. Okay, so line current is equal to under root 3 times of phase current. Again the power can be calculated with the same equation, 3 phase I phase cos phi. And there are some examples. Okay, I'll share this PPT and you can do this example at your home. It's very basic example. Just try it. If you don't, like, I'll give the solution as well. If you find any trouble, let me know. Otherwise, this chapter is done. So in this polyphase circuit, this is the only course. This is the only, like, whatever you have covered today is the only part of course. I'll share this PPT along with this example, so you can look into the examples. If you find any difficulty in the example, let me know. We'll discuss. If you have any difficulty during today's lecture, you can ask that or you can leave.
चैप्टर 7 खत्म.